Alright folks, this is going to be a continuation of the vector notes, so there was kind of a lot in there, so we broke it up into two parts. So we're going to start off the second half here talking about friction. I know we previously just finished talking about some vectors. We should have done everything from the top of vector notes, hypotenuses, sine, cosine, tangent, all that stuff, and I think we did all the vector addition. And we should have ended somewhere down here where you guys were finding vectors with a given magnitude in a direction from north. We're given a bearing and you guys were finding all the components, adding x and y components together and determining where the resultant vectors were. So this is where we left off from last week. So I'll start out talking about, we already talked about friction a little bit, but when we start talking about vectors and friction or two-dimensional forces and friction, it gets a little bit more complicated, but everything we talked about with the 1D stuff is still applied. So real quickly, it depends upon two things. One, it's the force of contact, like how much force is being applied between the two surfaces that are actually making contact, whether they're sliding or rolling. Sometimes that's a weight. If it's on a horizontal surface, it's the weight of the one object pushing into the other. But we're going to also talk about things on an inclined plane where gravity and the surfaces that make contact are not perpendicular to each other. So really it ends up being the force perpendicular to the surface that we really care about. So again, it's not always the weight, but it's the force between the two. And then the other thing has to do, the second thing friction really depends on, or how the frictional force is calculated, has to do with the coefficient of friction. And what that is it's basically, if you want to say how grippy something is, or the traction, or how sticky something is, it's the ratio between the weight, if you're talking on a horizontal surface, how much force is applied between them and how easily they slide across the surface. So like the force applied that it would take to either move the object from a dead stop, force of static friction, or how much force it would take to continue to get that block, or to continue keeping that object moving at a constant rate, which is also known as the force of kinetic friction. So here's some examples of some different measurements of mu. So remember this mu symbol here that's kind of how it's pronounced, is mu. Here's some examples, and it varies on the types of surfaces, not just the one surface but the other surface, because remember there'd have to be two objects making contact with each other. So if you have rubber on dry concrete, so that might be kind of like the bottom of your shoe or an automobile tire on dry concrete. It has a static mu of about 1.2. So that means it would take more force to drag the item across that surface than it would to pick it up. So it's more force applied, and that's a good thing, because obviously if you have automobile tires or your shoes, you want those to be grippy on a surface. You don't want them to be sliding all over the place. And then the mu kinetic for that is 0.85. Rubber on wet concrete, so assuming you're driving on a day and it's raining outside, or you're walking across a surface that is covered with water, the rubber on your shoe or the rubber on the tire beats concrete that has water on it. The static mu now, so from a dead stop, how much force would it take to get it to move, goes all the way down to 0.8, and the amount of force it would take to keep an object moving at that rate, once it's already in motion, is 0.6. And you'll see that some of these get quite dramatic. I mean, dry steel goes from 0.7 to 0.48 when it's not moving and is moving, and if it's lubricated, so like say you put grease on a bearing or oil in an automobile engine or something like that, where metals are rubbing together, it drops the static friction all the way down to 0.12 and the coefficient of kinetic friction down to 0.07. And it's good. Obviously, things that are moving all the time and making contact, like in an automobile engine or the bearings in your car, you do not want a lot of friction inside of those places, because it creates a lot of heat and resistance and energy loss and everything else. So, and then another one that's very, very slick is Teflon. If you guys have seen Teflon before, like on a cooking pan, like eggs or something, and cooking in a pan, its static and kinetic is approximately the same. They're both really low at 0.04. So when we go to calculate frictional force, and I know we've used this equation before, and this isn't really going to go away in two dimensions, it's still mu times the force perpendicular, which will look something like this. It's the same idea as saying frictional force is mu times force of gravity or weight when things are on a horizontal surface. So force of friction is basically the force applied parallel to the direction of travel, and this force perpendicular is again, the surfaces may be inclined now, so we call it force perpendicular. It could be on a horizontal surface, so it could be just pointed straight down, which would be the weight, but as you increase angles, that value is going to change because the weight does not push perpendicular to the surface as we go along. So I'll do some example problems for you guys, and I think you'll probably catch on as we go. So here's example number 1. Always follow the steps that you need here. You always got to list your variables, list the equation, and then solve. So we're going to do the exact same thing here. So they tell us a block of wood has a mass of 2 kilograms. It's being pushed along a smooth wooden countertop. It says if 5 newtons of force is needed to keep the block moving at a constant velocity, please find mu. Okay, so let's see what they give us. They give us mass, which is 2 kilograms, and they give us the force applied here. So this is the force to keep the object moving at a constant rate. That means this would be the force of friction kinetic, because the object is moving, so you're overcoming the frictional force, but it's the frictional force, kinetic frictional force, not the static. So this is 5 newtons, and that's all they give us. Then they ask us to find mu. So there's the variables that we got. We got mass, and we got the force of friction, and they want us to find mu. So looking at our standard equation that we got for force of friction, to find mu, you basically rearrange this equation and you divide force of friction by force perpendicular, so it's going to look something like this. Your mu is going to equal force of friction divided by force perpendicular. It looks kind of like that. So we know that the force of friction that they give us, so I'll list the variable, we know the force of friction that they give us is 5 newtons. So again, the object is in motion, but it's not accelerating. So thinking of Newton's second law of force as mass times acceleration, it's possible to have a net force of 0, but have an object to continue to move. It's just saying that the force you push with going in, say, this direction, if the object's traveling to the left, is equal and opposite to the frictional force going this way. So initially, to overcome the force of static friction or to accelerate, there had to be a greater force than the force of friction applied to get it up to that speed, but once it's moving, it's in balance, basically. The forces are balanced, but it's still in motion. So we're taking the 5 Newton frictional force, and we're going to divide it by the force perpendicular, which they don't directly give us, but we would have to figure out. So if you had a block of wood, and it is 2 kilograms, and they tell us that it is sitting on a horizontal surface, the force of gravity is equal to the force perpendicular because, so in order to figure out mu, we need to do the force of friction divided by the force perpendicular, but the force perpendicular is not given to us. All they do is they tell us that the mass of the block is 2 kilograms. So if we want to change mass into force perpendicular here, then we need to multiply the mass of 2 by 9.8 meters per second squared. So when we do that, we get 19.6 newtons, which is actually the force here. So basically what they're saying is you have to apply 5 newtons of force to move it, but the weight of it is 19.6. So I can see it's approximately a fourth of that. It's going to give us a little bit more than that. So the mu that they give us is 0.2, we'll go 0.255. Could round that to 0.26, but we'll say 0.255. And there are no units for mu. It's basically just a ratio. So that is approximately a fourth again, or 25%. So example number 2 is, so it goes something like this. We have 2 kilograms here, and then we have a smaller block on top, which is 1 kilogram. And they're asking us to find something else though now. They're asking us to find the force of friction kinetic, how much force it takes to continue to get the block to move. So let's see what they give us. We know the total mass, and I'm doing the total mass of the whole system because we're dragging this whole thing across, is equal to 3 kilograms. Mu does not change. It is going to be the same as whatever we had up here because the block that's on the bottom and the surface it's making contact with is exactly the same. So we're going to go 0.255, and then we're trying to find force of friction kinetic. So our force of friction kinetic, and we may need to do a little bit more work here, is equal to your mu times the force perpendicular. And the only thing here that's a little tricky is that, again, they only give us the mass here. They do not give us the weight or the force perpendicular. So if you're going to figure that out, you got to do the mass times 9.8. So we got a mass of 3 kilograms, and that multiplied by 9.8 gives me 29.4 newtons. So with that said, I'm going to do my mu, which is 0.255. And I'm going to multiply that by my force perpendicular, which is 29.4. That's going to give me 7.497, so we'll just go 7.5 newtons is the force that needs to be applied, which seems about right. It's approximately a quarter of what we had before. Then for example 3, it says for the 2 blocks, so the same as what we have up above, it says if there's a new force applied to it, so we're going to go with 10 newtons, they want us to find the acceleration of the block. So here's the thing to consider. If we're talking about acceleration and Newton's laws, we know that acceleration is equal to force divided by mass. The force that we use here has to be the net force, so it's the sum of the forces after all the friction and everything have been added to it. We do know that the mass is equal to 3 kilograms as it's stacked together. What we really want to find here is the force, and again, this is not just one of the forces applied, it is the total sum of the forces. So we have 1 and we have 2 kilograms here. Let's just say, for example, we're going to try to push the block this way. There's a frictional force going this way that's equal to whatever we just calculated up above. So 7.5 newtons. So let's just say that this is negative 7.5 newtons going this way. This is your force of friction kinetic. There's a force going this way now. We can call this the force applied, whatever we want. This is a positive 10 newtons in this direction. So in terms of a tug-of-war, this side is winning, and it's winning by how much? To find the force net, you're going to basically take the two, one being a positive, one being a negative. We typically call frictional forces negative, so this is going to give me a total net force of 2.5 newtons. So in order to figure out the actual acceleration, you take the net force and divide it by the mass. So our net force that we're using here is not 10 and it's not 7.5, it's actually 2.5 newtons. And if I divide all of that out, so I can put it here, 2.5 divided by the mass of 3, this is going to give me something a little bit less than 1. Gives me 0.83. This is meters per second squared. That would be the acceleration of the block. And then example 4, they're giving us a block on a frictionless surface apparently, so there is no friction, so this would be kind of like an air cart or something being launched across an air track. They give us the mass to be equal to 10 kilograms. The force applied is equal to 100 newtons. And if there is no friction, we don't really have to worry about anything else, because the force applied this way is the only force that's there. Now this is not typical for most real world scenarios, because there normally would be some frictional force going this way, but in this situation there is not. So we pretty much got it set up to solve without really having to do too many conversions. We take the Newton's second law here and we rearrange it to solve for A. If force is equal to mass times acceleration, then if we want to try to find acceleration again, we do force divided by mass. So if that's the case, we got 100 newtons and we got 10 kilograms, and 100 divided by 10 is just going to give us 10, and then the acceleration for this would be meters per second squared. For example number 5, they want us to find the acceleration of a box or a block that is sliding across somewhat more of a rough surface. So they give us the force applied and they give us the mass. So what we really need to find out here is we need to find the net force. So I know that the mass is equal to 10 kilograms. So that's the mass of the block. There's a force applied this way equal to 100 newtons. And then there's some force of friction over here. This is your force applied. And the force of friction is, in essence here, it's unknown. So we got to calculate that. So the force applied is 100. Our frictional force is going to be negative going the other way. And they do give us mu. They tell us mu is 0.5. So the first thing I want to do is I want to figure out this frictional force. So if that's the case, I find out my force perpendicular and my mu. So the mu itself is 0.5. The force perpendicular is not equal to 10, but it's equal to 10 times 9.8 because we got to change that mass into a force. So if I do 10 times 9.8, this is giving me 98 newtons. And if the coefficient of friction is 0.5, then the force of friction is going to be basically half of that. And we generally call frictional forces negative. So I'm going to say that this is a negative 49 going this way. So now we want to find the acceleration. Our force net is the difference between these two. I have 100 newtons going to the right and I got 49 newtons going to the left. So my net force is going to be 51 newtons, and that's important because when we go to find the acceleration, we want to take the total force and divide it by the total mass. So that's 51 divided by 10. So if that's the case, then we're going to have an acceleration equal to 5.1 meters per second squared. All right, then for example 6, this one has a lot of applications. So we got to find the net force, we got to find the acceleration, and then they also want us to figure out the distance that this object travels. So let's see what they give us. So they first say there's a hockey puck sliding across the ice. It has an initial velocity of 10 meters per second, so we're actually going to probably save that for the end. They want to know how far it's going to slide until it comes to a rest. So the fact that it's going 10 meters per second is great and fine, but what we really need to figure out is we need to figure out the acceleration. So let's see what they give us first. So they tell us the mass is equal to 0.5 kilograms. And they tell us that the mu is equal to 0.10. And we need to figure out the acceleration. And in order to figure that out, we basically are going to need the force of friction and the acceleration. So we're going to need all of these. So there is only one force acting on the object. It's moving this way with a velocity equal to 10 meters per second, but friction is slowing it down in the opposite direction, going this direction. So we need to figure out what that force is. So let's start there. So we'll take our force of friction is equal to mu times your force perpendicular. And again, they give us mu, but they do not give us the force perpendicular. Mu is equal to 0.10, and our force perpendicular is equal to the mass multiplied by the acceleration of gravity, because we are still dealing with horizontal surface. So the mass is 0.5 kilograms, and the acceleration of gravity is 4.9. And if I multiply those two out, this gives me 0.49 newtons, and this will be negative, because this is going to be slowing things down to the left. So from there we should be able to figure out what the acceleration is. So acceleration tells us the force divided by the mass of this item. So the force applied now, this is the net force, is a negative 0.49, and the mass of the total thing is 0.5 meters per second squared. So let's see, 0.49 divided by 0.5, it's really close to 1. it gives us negative 0.98 meters per second squared. Now, they want us to figure out the distance that the object travels. So we have a few options for this, and the choices are up to you. I'll show you one way, a way that I think is probably the easier of the two, and that would be to try to figure out the total time it's going to take for this to come to a stop. Because if we know the original velocity and we know the final velocity, which we do know, because the original velocity here is obviously 10, and at some point the velocity final is going to be 0. If we know the change in velocity, we should be able to figure out the time, seems how we have acceleration. And if you have time and velocity, we should be able to figure out distance. A little bit of manipulating with each, but it shouldn't be too bad. So if we know acceleration, acceleration is equal to change in velocity divided by time. So if you want time, you move it over here and you do change in velocity divided by acceleration to figure this out. So we know it's going to change by negative 10 meters per second, and we know that the acceleration is negative 0.98. So you can see that this is going to give me something really close to 10 seconds, but it will be a little different. 10 divided by 0.98 gives me about 10.2 seconds. And to try to figure out a distance, we have velocity average multiplied by time. How far does it go multiplied by, or what's the rate that it's going, how many meters per second, multiply that by the seconds or the time, and it should tell us how far it goes. Now, a common mistake is people would probably say, okay, it's going 10 meters per second, so let's multiply that by 10.2, and say it goes 102 meters. Well, it's not going 10 meters per second the whole time. It starts out at 10 and ends at 0. The velocity average, assuming the acceleration is constant, which here we are, the velocity average ends up being somewhere dead in the middle. And in this case, it would be equal to 5 meters per second, because we know it starts at 10, ends at 0. Halfway in between is going to be equal to 5. You can always assume that as long as the acceleration's constant, which in this situation, that's our assumption. So now I can just take my velocity average of 5 meters per second, and I can multiply it by the time of 10.2. And if that's the case, I'm going to be set with 51 meters. So with our next example, we're going to be talking about forces on a ramp, or forces that aren't always perpendicular to each other. So things get a little bit more complicated here, because our perpendicular force is no longer the same as your weight or your force of gravity. So what we end up doing is, if you have something sitting on an incline, we got to use a little bit of the trigonometry that we've been learning to try to figure out some of these forces and some of these vectors. So you'll see that the hypotenuse of this triangle is equal to f of w, which this is always going to be the same as mg. So whatever the mass of the block is multiplied by the acceleration of gravity, that's basically what we got there. So that one's probably the easiest to figure out. However, we have two other forces. We have a force parallel and a force perpendicular. So the force parallel is the same as our, say, force applied, which is going to be in the same direction, equal and opposite of our force of friction, which would actually be going up the ramp. But once you find those forces out, we then really can use the same equations as anything that we had before. So what are your equations here? Well, let's see. We know the hypotenuse. That'll always be the easiest thing to calculate. For force perpendicular, and here is the theta that we're using, because whatever angle above the horizontal you get is the angle away from the perpendicular that we're going to get here. So if this is my angle up here, this is my adjacent side, and this is my hypotenuse. So that's going to be using the cosine function. So if that's the case, I'm going to be doing force of weight, F of W, multiplied by the cosine of theta for this. And down here, I'm going to be doing the F of W, force weight, times the sine now of theta, because this is my opposite and my adjacent sides. So with those put into place, we should be able to figure out some of these calculations. So I'll do a little bit of that here and we'll see how it goes. perpendicular and our force parallel. So let's just take a look at that. So our force perpendicular is the force weight multiplied by the cosine of theta. So if that's the case, I'm going to do 400 newtons, and I'm going to multiply it by the cosine of theta, which they tell us here is 27. And just plug that into the values here and see what you get. So we do 400 times cosine 27, and again, make sure that your calculator is in degrees and not radians. So this gives me 356.4 newtons. So that would be how much force is being applied this direction. And then for the next one, we're doing force weight divided by the sine of theta. So we're going to take our 400 and we're going to multiply it by the sine of 27 degrees. And this should give us a smaller value here because, it's less than 45, so our, force perpendicular pushing into the surface is going to be greater than the force pushing across the surface. So we'll do 400 here times the sine of 27. This gives me 181.6 approximately. And then they're asking us for the force normal. Well, the force normal in this situation would be the same as your force perpendicular, because remember, the normal force is always the force between, the two surfaces, or the contacts between the surfaces. So we really don't need to recalculate this. We just know that the force normal is equal to our force perpendicular. So this is our 356.4 newtons. Then they want us to figure out the acceleration of the object going down the ramp. But then down here they want us to find the acceleration of the object going down the ramp. Here it says ignore friction. So if there is no friction there, then acceleration again is just equal to force divided by mass. If there's no friction going up the ramp, the only force that's applied to the block is the one pushing it this direction, which is the same as our force parallel. And again, in reality, there probably would be some friction going this way, but according to the problem that we have here, that is not the case. So our force parallel is the 181.6 newtons, and the mass of our block that we have here is equal to 40 kilograms. So we're going to take the one, gives us an acceleration of 4.54 meters per second squared. And in example 2, they're going to ask us to do the same thing, except this time they want us to figure out how the coefficient, or how friction would slow this down. So they give us a mu equal to 0.10, and we're trying to figure out the force of friction going up the ramp. So it's going to be equal to mu times this force perpendicular. So I got 0.10. Which is a very low coefficient of friction, equal to the multiplied by the force perpendicular here. So that's the 356.4 newtons. So if I multiply that by 0.1, this gives me 35.64 newtons. And this is a frictional force, so in essence this is going up the ramp. So if you think of it this way, we have the force parallel going this way, and the other direction now is this 35 that we got going down the ramp. So if you think of this like a tug-of-war, we got the force going this way, which we have already said was equal to 181.6, and then going this way now we have a small force of 35.64. So consider this one a negative and then consider this one a positive to figure out your net force, because that's what we really want. So the net force is equal to that 181.6, which we used in the previous example because there was no friction, and I'm going to subtract 35.64, and this gives me a net force of 145.96. So to figure out our acceleration here, we're going to do the force net, which is less than our previous problem. I'm just going to use 146 here. We'll round this to 146. That's the net force we have, and then the mass that we had from the previous problem. Same thing, mass doesn't change, it's still 40 kilograms. So I'm going to do 146 divided by 40, and this gives me 3.65 meters per second squared. So without any friction and with a coefficient of friction to be equal to 0.10. First one for our mu static, we know that the angle that it slipped at was equal to 40 degrees. So I'm just going to plug in the tangent to 40 degrees for that one. Again, make sure your calculator is in degrees and not radians. And this gives me 0.84 approximately. Then if I want to find the mu kinetic, it's still just equal to the tangent of theta. Just notice that the criteria changed a little bit because they do say that the ramp is lowered and you have to give it a little bit of a nudge. And that nudge is overcoming the static friction, but once it starts to move and it's kind of maybe bouncing along those microscopic ridges, it continues to carry on in motion. So for this one here, we're going to have the tangent of 25 degrees. And if I multiply that out, I get about 0.47 if I round it. And that's about it for this week. So if you guys have questions, please feel free to send me an email or stop by, and I can try to help you guys out one-on-one. Otherwise, have a good week.